Okay, gravity gradients continued. The basic idea was if you have some shape in orbit, here's Earth, here's a dumbbell shape, just to make life easier. The part that's closer to the Earth is going to have a slightly stronger pull than the thing that's slightly further from the Earth. And so this will lead to, in this case, right, if there's a center of mass right here, this would lead to a restoring torque to the upright position. There's other equilibrium positions. If we had this completely parallel to the horizon, then both forces would be equal. There'd be no torque. But then think about if you shift this a little bit, then one goes closer than the other, and now it's destabilizing. So it seems like, at least for the dumbbell satellite, one of the orientations, think of perfectly parallel with the radial vector. It looks like it's going to be stable because anything offset is going to make it balance. Whereas if you're like this, that's also an equilibrium, but any little offset is going to make it want to grow. So we want to eventually get to conditions for equilibrium for any kind of rigid body, and then whether or not they're stable or unstable, and maybe even some quantitative information about what's the frequency of wobbling about an equilibrium. So that's what we're heading towards. So let's do that. And if you remember where we ended last time, we were doing an analysis of the moment on some rigid body. We were looking at individual masses, and then here's the Earth again, and some radial direction to the center of mass, and then a contribution due to each of these other little pieces. So here is our center of mass. And what we had gotten to was that the torque or moment due to gravity, which close to Earth, we totally neglect this because it's so small. But out in space, because there aren't that many environmental forces, it can be a large effect and can be used to stabilize satellites. The moment to gravity, we'd gotten to L sub G, LG, moment due to gravity. This was GME, so that's the mass of the Earth. G is the gravitational constant. And then we had RC cross, and then integral over the body. So this is the body, integral over the body, little r, big R to the third dm, and we had gotten to 1 over big R to the third, the magnitude. And what is this? Big R to the third. That's the from the center of the Earth to each little piece in the body. We wanted to approximate that. So it's approximately 1 over the scalar distance from the center of the Earth to the center of mass raised to the third power. And then the leading order term was 1 minus 3 RC dotted with little r over RC squared. So we'll keep this leading order term. The other term was like a factor of 1,000,000 smaller. So we just want to keep the leading order one. So that means that the gravity gradient torque, let's pull out all of the constants, G and E. And we're going to assume for now that the satellite's on a circular orbit. So that means RC is going to be constant. It's not going to change in time. So we've got G, mass of the Earth, RC cubed, RC the vector across now this integral with this substitution in there. We've got R 1 minus 3 RC dotted with little r over RC squared. That's to leading order. Now, if we break up what this integral is, the first part of the integral is going to be R dm, and then the second part will be so that's just the integral. This will be minus integral, little r, r dotted with RC dm. Maybe I'll do a plus and then put the minus inside that integral term. Okay, so this is the integral. To sort of expand it into its two parts. This part is 0. This is something that we referred to many lectures ago as the center of mass corollary. Right? We're basically summing up what's the contribution of each mass with respect to the center of mass, and that gives us 0 because the center of mass, it's just telling us where's the origin in the center of mass centered frame. So that's due to center of mass corollary. I think back when we were talking about multi-particle systems, but it still holds for rigid bodies. So good, that goes away. And then we're left with this strange vector times a dot product. So what are we going to do with that? We can use a vector identity. There's this vector identity of A cross B cross C for any 3 vectors is A dotted with C times B minus A dotted with B times c, which we can then rewrite as negative a dot c b equals negative a cross b cross c minus a dot b c. So we're just rewriting this vector identity that you could look up, but then we'll use certain things for a, b, and c. So this will give us minus little r dotted with rc. So that dot product times little r equals negative little r cross little r cross rc minus r dotted with rc. You might wonder, why are we doing this? Well, here we're getting an r cross r, and then we would use, instead of the cross product, we'd use that kind of cross product equivalent matrix, the tilde matrix. And what you're going to see is we're going to get out of this the moment of inertia matrix, which kind of makes sense. You would expect that the gravity gradient is going to have something to do with the mass distribution inside a body, and the moment of inertia matrix is that mathematical object, the 3x3 matrix that does describe the mass distribution inside a body, a rigid body. So will be used to get moment of inertia. But let's substitute it in. We're starting from up here and then plugging everything in that we have. Moment due to gravity. I think I'm missing a factor of 3. Is there a factor of, there's a factor of 3. So we'll have 3 gm over rc, now raised to the 5th power. Is that right? I guess I forgot another thing here too. Raised to the 5th rc squared. But that's a constant. It's not part of the integral. So it could be brought out. Rc to the 5th. Rc, the vector, cross integral, negative r dot r times rc minus r cross rc dm. If we do this first integral, capital RC can be brought out of the integral, and then we'll have RC cross RC. So that's going to give us 0. And then we have this other thing where we can't pull out RC. So what do? So this is going to be 3gm over RC to the 5th, RC cross, and now we've got the integral of minus r cross rc, which we will rewrite little r tilde rc dm. And rc isn't part of the integral, so it could be brought out. Now we've got this. And then maybe at this point you could recognize, what is this integral? This is the definition of the moment of inertia matrix. So that's pretty cool. So that means we've got the torque due to gravity is 3g mass of the earth rc raised to the 5th rc cross moment of inertia matrix times rc. So this is the gravity torque on a rigid body to leading order. The other terms are so much smaller that they are basically irrelevant. So this is the main effect that you would have. And you could maybe try to figure out, what's the order of magnitude? Is it like millinewton meters? It's small. It's small. We haven't specified, even writing it here, we haven't specified which vector coordinate frame we're using. We haven't specified that we're using a body fixed frame or an inertial frame or maybe some other frame. So at this point, haven't specified the frame. We could, and there is a very useful frame, the frame of the orbit. So if we use the frame of the orbit, then this is pretty helpful because the orbit is the thing we care about, right? So we're going to introduce this frame, and this might be different than other orbit frames that you've seen. Right, so we've got this RC vector going from the middle of the Earth to the center of mass of the spacecraft. And then we have O3 is in the radial direction. So pointing out away from the Earth. It's the unit vector in the radial direction. O1 is along the orbital path. And then O2 is the orbital plane normal. So this frame, call it maybe big O, and it's O1, O2, O3. Those are right-handed, right? O1, O2, O3. I have my Earth. Here's my Earth. The radially outward, that's O3. O1 is along the orbital path. And then O2 is normal to the orbital plane. Now, is that an inertial frame? No, it's not an inertial frame. It's rotating, right? Those directions will rotate around at the same rate as the orbital rate. And it'll be rotating about O2. If you were in this frame, you'd see this, each orbit go around once. So this is not an inertial frame. It rotates with respect to an Earth-centered inertial frame, and we don't need to specify if it's like the Earth-centered ecliptic or Earth-centered equatorial. We'll call whatever that frame is N. So somewhere down here, there's an inertial frame, but it rotates, and it rotates with some omega O with respect to N. So it does rotate. And in fact, how would we get that? Omega O with respect to N is going to be, I'll call it capital omega about the O2 direction, or the orbital angular rate. Omega is from Kepler's law. Omega equals Gm mass of the Earth. We're thinking of circular orbit, so RC is the same as the semi-major axis, and that's raised to the cube, and we'll take the square root of that. And this is in radians per second. So that's the frame we're introducing. And in this frame, another thing to note is, what is RC? Right? RC is going to be little rc in the O3 direction. Or if you want, if we write it as a column vector, 0, 0, RC. Now, typically, rigid body dynamics that we've done are written in the body frame, B. So we could write the center of mass position vector in the body frame as well if we wanted to. If I had a body frame, B3, B1, B2, something like that. So that's a frame fixed in the body as it's moving around. So in the body frame, we could write RC. It's going to have 3 components typically, and that's a bummer, but oh well. So we'd say RC1, RC2, RC3. And then using how we know to relate reference frames, right? If you have a vector written in the B frame, the direction cosine matrix, BO, column vector 0, 0, RC. Because then we're multiplying times what the RC vector is written in the O frame. Okay, now combining all of this with what we have for the gravity torque on a rigid body, we've got everything we need. And we have a choice of what body frame. Let's use as our body frame a principal axis frame, because that's the most convenient choice. And why do we want to do that? That's just so that the moment of inertia matrix will be diagonal, I1, I2, I3. The moment of inertia about B1, B2, and B3 directions. Then the gravity torque, LG, is 3gm over RC raised to the 5th times, and now we'll write RC written in the body fixed frame. And then that'll be cross this inertia matrix times RC written in the body fixed frame. But we could carry out that matrix multiplication. We're writing the result in the body fixed frame. So maybe we'd call this LG1, LG2, LG3, the 3 components as seen in the body fixed frame, 3g times mass of the Earth, RC to the 5th, and then this vector, you carry that out, you get RC2 times RC3, I3 minus I2, RC1, RC3, I1 minus I3, RC1, RC2, I2 minus I1. So this is what the gravity torque looks like seen in the body fixed frame, right? Here's the body fixed frame. The torque is going to be something. And as this body moves around, you know, the torque will also maybe also change. Equilibrium would be where the torque is equal to 0. So what are the conditions for the torque to be 0? That's equilibrium. And that's probably what we want our spacecraft to be operating in, some kind of equilibrium configuration. Well, to get that, what do we need? We need all these components to be 0. So this would happen if all of them were equal. If all of them are equal, then we have a sphere. So something that's spherical, or it just has a symmetry to the mass distribution so that all the moments are equal, like a perfect cube, then you would have no torque. You'd have no torque, but in any orientation, which also means that there wouldn't be any restoring torque. So you don't ideally want a situation that's symmetrical. And fortunately, most spacecraft are not, but that's not good because there'd be no restoring torque because the torque is zero in any orientation. Hopefully you see that. Another one would be is if, and maybe this one is harder to see. So this also would occur, meaning we would have zero torque or equilibrium if RC is aligned with one of these body fixed directions, any one of them. So let's say if RC was aligned with the, here's B1, B2, B3. If it was aligned with the B1 direction, then that means RC1 is non-zero. RC2 and RC3 are both zero. So all of these would be zero because they multiply something that's zero. So that's kind of cool. As we're in orbit, if one of the, let me get my Earth again. Earth, welcome. So here's Earth, and here's some radial direction. If all I need is one of my body fixed axes pointing in that radial direction, or just it just has to be parallel with it, so I could be pointing opposite as well, and those would be equilibrium configurations. So now we know something. Yay, that's good. That basically means having a principal body axis aligned with the orbital radial direction, which in our little schematic was, we called that O3, I think. If I were to go up here. Yeah. So if any one of these, B1, B2, or B3 is actually aligned with O3, then we have an equilibrium. They're called relative equilibrium states. Why do we say relative? Because it's not an equilibrium with respect to an inertial frame. It's an equilibrium with respect to this rotating frame, the orbital frame. We want to write down what the rigid body equations of motion are. Let's see if we've got this right. I'm just going to write, instead of I sub C, I'm just going to write I. This makes it easier. Moment of inertia is going to be about the center of mass times omega of the body frame with respect to the inertial frame. We've usually just been suppressing that because we've only had one rotation that we're dealing with, but now we've got two. Rate of change of omega, maybe I'll put that diagram again, of the Earth. Here's O3. O1 is along the orbit, and then O2 is perpendicular to the orbital plane. And then we've got these B directions. I don't know what they are exactly, but we've got these two frames. Actually, we have a third frame, the center of the Earth frame. We've got a body frame, the orbital frame, and an Earth-centered inertial frame. So the rigid body equations of motion are I times the rate of change of omega of the B frame with respect to the inertial frame, plus, these are just Euler's equations that we've written before. So there's nothing hopefully mysterious about it. I'm writing the omega cross, but instead of omega cross, I'm writing omega tilde because it's easier. Moment of inertia, omega Bn. And now when we were talking about free rigid bodies, on the right-hand side, there was zero, but now it's not zero. It's the moment due to gravity. And how are these angular velocities related? The angular velocities related by, we've got omega of the body with respect to the inertial frame, and that's equal to the rotation of the body with respect to the orbital frame, plus omega of the orbital frame with respect to the inertial frame. So relative equilibrium would be what? We've already worked out what the orbital frame with respect to the inertial frame, that goes back to orbital mechanics, and that is omega O2. That's from orbital mechanics. Omega of the B frame, the body frame with respect to the orbital frame, we want this to be zero. So this is the relative equilibrium condition, right? Because that's what matters for satellite operations. You don't want to be kind of fixed with respect to the inertial frame. You usually want to have some part of the spacecraft pointing towards the Earth, meaning you want to be not rotating with respect to that orbital frame as the orbital frame goes around. So that's why we call it relative equilibrium. I mean, what's actually happening is the spacecraft is rotating at the same speed as this orbital angular rate, capital omega. That's what we want. It's just like the moon, right? The moon is always showing us one side. So the moon, we don't get to see the far side of the moon. The moon is locked, so it's called tidally locked. The orbital period of the moon is 1 month, and the rotation rate of the moon is the exact same thing, 1 month. And we want to just do that for spacecraft, figure out how to work that out. So we've got these equations of motion. This relative equilibrium condition, we've got that. We've also figured out, what was this up here? I said this was the condition for relative equilibrium. It's another condition. This was the condition that led to the torque being 0. So we've got this as well as this. So we might say these. Let me set this equal to 0. This is also necessary. We said that RC had to be aligned with one of the principal axes, which means O3, the O3 direction is in one of these directions. We'll just say O3 is in the direction of B3, okay? For sake of argument, O3, B3. You could have O3 being in B2 or B1 or negative B1. Those would also work. But just to do the mathematics, we're picking one of the directions, calling that B3. We haven't yet said what's like the maximum, intermediate, and minimum inertia directions. We haven't got to that yet. We're just saying, if I call this my B3 direction, and this is my orbital directions, then I'm just saying these are aligned. The third axes are aligned. Maybe not the other two, at least the third one is. The LG, moment due to gravity, being 0 implies that you must have a principal axis in the O3 direction, and we're just picking B3. So if we were to write the moment of inertia, we could write it in the orbital frame. It's changing its distribution in the orbital frame. If we're always saying that B3 is in the O3 direction, then this will be a block diagonal matrix, meaning we'll have something that looks like this, I22, and then we've got these pesky I12s because there's possibility of rotation. The orbital directions are not principal axis directions in the O1 and O2 direction necessarily. That can be a problem. We want a relative equilibrium, and we want it to stay a relative equilibrium. So the angular velocity condition, omega b back to O, is 0. But we also want that that's not changing. So omega b with respect to O, time rate of change. So dot is 0. We can't change orbital mechanics, not yet. So we'll say that this is equal to omega in the O2 direction. But then we also don't want that to change, but it doesn't change. That's, again, orbital dynamics. Okay, so we've got that. I'm looking at this equation. Omega b with respect to n, we've got this equal to 0. And then we've got this equal to omega O2. And we have omega dot. So what are the omega dots? They're both 0. That's cool. So that means up here, this is 0. And this has got to be 0 torque. So that means we're just left with this thing equaling 0. So what is that? So we want that to equal 0. This is the condition. If you work out the matrix multiplication, this gives you, in the orbital frame, 0, 0, minus I12 omega squared equals 0, 0, 0. That's what we want. Which either means we set omega equal to 0, orbital angular rate goes to 0 as you get further and further and further away from the Earth. But then what's the point? So the other one is I12. So this means I12 equals 0. So what does that mean? If I12 equals 0, that means that the relative equilibrium must have all principal axes aligned with the orbit frame. So for the relative equilibria that we want, meaning the spacecraft is not changing its orientation, then we need all principal axes in the body aligned with the orbit frame. So hopefully you get what I mean. Here's the Earth. Here's our orbit frame. What we need is the principal axes to be aligned. And you could be anti-aligned. There's a bunch of different configurations that will work. That's a equilibrium. We don't yet know if they're stable. And by stable, we mean if you perturb a little bit, will the gravity torque restore it, or will the gravity torque take you further away? So we need to consider that. So this would be the next thing, which is linear stability about these equilibria. let me just bring in that picture of the orbit frame. For this orbit frame, we could describe the orientation of the body using yaw, pitch, and roll. It's not the convention that we've seen where Z is down. We're using this orbit frame, but still roll is going to be about 0.1, pitch will be about 0.2, and yaw is about 0.3. So if I've got my space shuttle, you might be thinking, oh no, I have to have 0.1 in the direction of the nose of the craft. Not necessarily. We're just picking these directions because they're convenient to work with, right? And we're saying this, I would say, let's call this 1, 2, and 3. So we've got roll, got pitch, and then we've got yaw. We're going to use the 3, 2, 1 Euler angles to describe the orientation of the spacecraft. The body fixed frame, the B frame, with respect to the orbit frame, where roll is about 0.1, pitch is about 0.2, and yaw is about 0.3. We want to study what the yaw, pitch, and roll motion are. And then we'll make an assumption later that we're only looking at very small yaw, pitch, and roll motion. And then we'll get some equations of motion. So from rigid body dynamics, we've already written what omega B with respect to O, right? We're writing in the usual 3, 2, 1 yaw, pitch, and roll Euler angles. So we've got this. I'm going to move it over here. There we go. So we're writing yaw, pitch, and roll. Roll, it's the same sort of thing. We're using V, theta, and that. And then we write them in this order, the yaw angle, and then pitch, and then the roll. But if you remember the way of relating omegas, what is this? This is omega 1, omega 2, omega 3, written in the body fixed frame. The relationship between that and the time rates of change of the Euler angles, it's not just they all equal each other. There's this pesky matrix, B inverse. The spacecraft angular velocity relative to the inertial frame would be omega Bn equals omega Bo plus omega On. And if you're saying, well, hold on, I thought you said omega Bo equals 0. Yeah, well, now we're letting it adjust. The earlier thing was for finding equilibrium. Now we want to find the linear stability about equilibrium. So we need to let that change. We're also going to need, because omega On is capital omega, the angular rate of the orbit frame. This is written in the orbit frame components, but we want to be able to write this in B frame components. And so what is that? It's B with respect to O, omega On. So that means we need B with respect to O. But we said we're using the 3, 2, 1 Euler angles. So we already have what that formula is. There it is. We're just using the shorthand notation of C, S, and all that. So this is B with respect to O, using yaw, pitch, and roll. The 3, 2, 1 convention for the C matrix, the direction cosine matrix. All right, now using this in here, what do we get for omega of O with respect to N, B? This will be, pull out a capital omega. We're just basically writing what the O2 direction is in terms of the B frame. And it's C theta S psi S V S theta S psi plus C V C psi C V S theta S psi minus S theta C psi. What we've done is just picked out the second column of the BO. And if you remember what the definition of what B and O would be in terms of dot products of B directions and O directions, that makes sense. So this is what we've got. We'll add this to this one here so that we get the overall B with respect to N. So we could do rigid body dynamics. So omega, right, B with respect to N is omega B with respect to O plus omega of O with respect to N. We're writing all of these now in the body fixed frame. And so what will it be? Let's just work it out. It's not pretty, but we'll make some simplifying assumptions. S psi dot plus C phi theta dot plus omega times a bunch of stuff. Oh no, I'm running out of room. Oh no. No, there it goes. Okay, great. And then more stuff. I'm just transcribing from these formulae plus omega c s s minus s c. Whew. So this expression is valid for any large rotation of the spacecraft with respect to the orbit frame. But next, we want to look at a small rotation. So this is true for large rotations. I mean, arbitrary, small and large. But we're going to make an assumption now, a small angle approximation. We only want to look at yaw, pitch, and roll angles that are small, because what we want to know are small deviations from equilibrium. Small deviations from equilibrium will correspond to small yaw, pitch, and roll angles. So to study stability of equilibria, we can assume all of these are small. Yaw, pitch, and roll, all small, which means we could set cosine of anything basically equal to 1, and then sine of whatever it is just equal to, just get rid of sine. And so you'll notice everywhere that we've got, we will only keep linear terms, only keep terms linear in small numbers. And if you do that, that's right, things like sine times sine will be theta times psi, which is small. So we would just ignore that term. We're also going to assume that the angular rates are small, so also small. So what we're left with will be omega b with respect to n, written in the b frame. From now on, we'll just call this omega because it's easy. It's omega 1, omega 2, omega 3. This is going to be, when we make this assumption that things are small, the only thing that survives, phi dot plus omega psi, and then we'll have theta dot plus omega, and then psi dot minus omega phi. Now, if we take the derivative of this, omega dot, so that means time rate of change of omega. This is now equal to about, we just take time derivatives, phi double dot plus omega psi dot, theta double dot, and then psi double dot minus omega phi dot. And then we could use this in the rigid body equations of motion. I omega dot, and I'll just rewrite it, minus omega tilde I omega plus the moment. This is written in the B frame. And we have to stop there, but that's where we'll continue next time to get the linear stability. All right, I'm out.